thank you very much. It's a real pleasure to be back at CITA. So the topic of my talk today, indeed, are various classes of theories of the very early universe. And the emphasis that I'm going to give is that, in fact, these theories are distinguishable because they have predictions that are robust in the sense that they're governed by symmetries. So symmetry principles will play a big role in trying to disentangle these different ideas and how to test them. So, of course, all of modern cosmology rests on the Big Bang model. The Big Bang model says that at some moment, some 14 billion years ago, the universe, all the matter that we see, and space as well, and time, all started out at a particular moment and expanded out thereof. As the universe expanded, it cooled. As it cooled, it underwent periods of radiation domination, matter domination, and eventually its structure formed. That's the standard picture. And of course, that standard picture is not ruled out. A Big Bang model of the kind I just described, since our universe today, extrapolated backwards in time, consists of many causally disconnected regions, a generic outcome of a Big Bang model would be various different parts of the universe having wildly different temperatures, wildly different densities, not at all what we observe today. So a critical addendum to the picture is inflation. Inflation takes a smooth patch of the universe, blows it up by an exponential amount, thereby creating a large universe. It's no longer a wild speculation. It's part of the standard model. Of course, a logical alternative that we'll explore in this talk is that, in fact, the Big Bang did not need to be the beginning of time. It could have existed before the Big Bang. The universe could have existed in a long phase of contraction, could have existed all the way to t minus infinity. And if you imagine that picture, then it's clear that there's plenty of time for the universe to homogenize itself on the largest possible scales. We'll explore both of these alternatives. And in fact, the main message is that we can distinguish, hopefully, with future observations between these different ideas. So this kind of optimistic message, of course, comes about because of its rapid progress in observations, particularly microwave background observations. So it's worth keeping in mind some milestones. We're approaching the 50th anniversary of the discovery of the cosmic microwave background by Finnis and Wilson. That was, of course, a long time ago. In fact, to put in perspective, so long time ago that it's about the same time as the last time the Maple Leafs won their last Stanley Cup. Sorry, I couldn't help that. A more recent milestone, more recent memory, was the discovery of the temperature anisotropies of the microwave background by the Khoury satellite. And you can tell where I'm going with this, of course, might be Montreal Canadiens. That was their last Stanley Cup. More recent memory. Some 10 Stanley Cups in between for the Canadiens. Since then, there's been tremendous progress in the microwave background data. We went from Khoury to this beautiful, exquisitely accurate map of the WMAP satellite. And of course, upcoming will be the Planck data. So this is a very exciting time, and it leads us to be very optimistic. In fact, as theorists, it's led us to be perhaps a little bit too overly enthusiastic. We're an enthusiastic bunch, because if you give us good data, we're going to get very enthusiastic. So this is a zoo of inflationary models that theorists have come up over the last 30 years. They all come with their own name and exotic physics. And of course, it's a fine exercise to pick any one of your favorite models and test this model against the data. That's a fine exercise to see how well it does. However, the inverse problem of taking the data and trying to reconstruct the potential, reconstructing the potential, it's fair to say has been met with mitigating success. The reason is simple. We can only constrain, first of all, with a microwave background, only a few parameters of the perturbations, of the potential, the slope, and the curvature. And we also have access to a finite range of modes to the microwave background that correspond to a finite field range of the potential. So in general, there are many potentials, there are vast degeneracies in terms of how many potentials can fit the data. But there's a more fundamental problem, you see. Once you start drawing this curve, you're making crucial assumptions about the microphysics. You're taking seriously the idea that inflation was driven by a scalar field, that it was driven not only by a scalar field, but a canonical scalar field, with canonical kinetic energy, and that it was driven by this kind of potential. These are additional unnecessary assumptions, in my opinion. So instead, in any case, we're not so interested to find the precise potential, although that would be great. We're really asking very fundamental basic questions. First of all, did inflation actually occur? And if it did occur, how many degrees of freedom, how many fields participated? Was it only a single field that was both driving the background and generating density perturbations? Or were there many fields participating in the dynamics? Or is some other dynamics, like the pre-Big Bang story I alluded to earlier, responsible for the observations, and how can you tell the difference observationally? So the approach we're going to take today, and I think it's the approach that's becoming more and more present in the community, is to instead focus on broad classes of theories distinguished by their symmetries. That's of course a well-trodden path in particle physics in the 60s, where people were confused about the strong interactions. People focused instead on trying to deduce properties of strong interactions based on symmetries, in particular the parallel Lagrangian proposed by Weinberg to describe pion physics. These are very powerful methods. And I want to claim that it's a very useful, I think, approach to cosmology, precisely because we happen to live in a universe that has a lot of symmetries. I think it's a promising way forward. Let's start with the symmetries of the background. So our universe, of course, on the largest scales is exquisitely homogeneous and isotropic. This is the data, actual data from the Khoury satellite, showing that the temperature across the sky is isotropic to 1 part of 10 to the 5. It's quite remarkable. And as long as we don't live in a special place in the universe, it should also be homogeneous. Which means that our universe actually can be described by a rather simple mathematical model, namely the Freeman-Robertson-Walker-Lemaître model given by this metric. The entire dynamics of our universe is governed by a single function of time, the scale factor. And moreover, the spatial geometry at any given time is fixed to be rather simple also. It's any of the 3 maximally symmetric spaces in 3 dimensions, which are the sphere, the 3 hyperbolic geometry, and the plane. So a very simple universe indeed. And in fact, the data, in particular the boomerang data, of which CITA played a major role, showed the convincing evidence that in fact our universe is supposed to be flat. The radius of curvature of the universe has to be of the order of 10 times greater than the size of the universe. So it's very close to being a plane, which you could argue is even the simplest possibility of these 3. They're all as symmetric as one another, but if you happen to be on this one, you have to explain why is the radius of curvature happening to be the same as the observable size of the universe today. It has some coincidence to the plane. The plane is a simplistic possibility. So that's the status of our universe. And the typical answer to why the universe looks the way it is because of inflation. So what's inflation? Inflation is a phase of, in a nutshell, a phase of quasi-de Sitter expansion with a clock. So in the simplest case, it's driven by a canonical scalar field with a potential. And if you model it as a fluid, it has both an energy density and a pressure. Its energy density is the sum of the kinetic and potential. The pressure is the difference of the kinetic and potential. And we can also assign it an equation of state, W, which is the ratio of pressure to energy density. And inflation takes place if the scalar field happens to be in the part of its potential where the potential happens to be flat. In that case, the field is slowly rolling. And if it's slowly rolling, its energy density is dominated by the potential energy. And that potential energy is approximately constant during the clock. This corresponds to an equation of state, which is approximately -1. So the constant energy density looks like a cosmological term. If you plug that into the acceleration equation, it gives you an acceleration which is constant, and as a result, and it's positive. So, oops, sorry. It was a little fast forward. So if you plug it in, you get an accelerated expansion. The acceleration is positive, and as a result, it's actually an exponential expansion, which is the Sitter space. That, if you want, is just the Sitter space. Exponential expansion. Why does this address the homogeneity and isotropy of the universe? So here's a nice heuristic argument. Actually, it's more than heuristic. It's pretty rigorous. Let's imagine that we're going to throw in a variety of different components, energy components, into the Freeman equation. So this is a very general Freeman equation where the expansion rate is governed by various energy matter components. And I've allowed for all sorts of things. I've allowed for some non-relativistic matter, which goes as 1/8 cubed, radiation, 1/4, some spatial curvature of the universe, which scales in this fashion. I even allow for anisotropies, which gives you a contribution which is 1/8�6th in the Freeman equation. And we've also allowed for a scalar field component, which, for simplicity, I'm modeling as having the constant equation of state W. That's this guy. In a normal Freeman-Robertson-Walker universe, since the universe is expanding, the most dangerous term of all of these is the one that redshifts the most slowly, the slowest. Namely, the one that has the smallest power of the scale factor, in this case, this guy, the curvature. And that's the flatness problem. An expanded universe tends to be dominated by curvature at late times. So if you want to avoid curvature domination, what you require from the additional term, this inflaton or inflationary component, is that it has to redshift even more slowly. That power here has to be less than 2. In other words, the equation of state has to be less than minus a third. And if you recall the acceleration equation, a component that has an equation of state less than minus a third corresponds to accelerated expansion. That's inflation. As a result, as the universe expands, if you have such a component, it will tend to win out over the curvature, it will make the universe flat. And in fact, it will also win out over everything else. It drives the universe to be isotropic, to be empty, and so in fact it's a dynamical attractor. That's how inflation, if you want any component which has this kind of equation of state, can drive the universe to be smooth and symmetric. There's another possibility, which we're also going to explore. Let's consider a universe, for concreteness, that existed before the Big Bang. Let's suppose the universe exists before the Big Bang, and it's collapsing. Now, a universe that's collapsing implies that the scale factor is shrinking towards 0. The universe is shrinking, the scale factor is shrinking towards 0, not the most dangerous term is which one? The anisotropy. It will be the one with the highest power of the scale factor. And that's intuitive. The universe that's collapsing tends to become increasingly anisotropic. And in fact, as was shown by these authors, you can even enter a chaotic regime. So some dimensions will start contracting at different rates, some of the spatial dimensions, and some of them can start expanding in some chaotic failure motion. So it's a very dangerous term as you approach a big crunch. So to avoid that, what you would like is for the additional component in this case, some scalar field component, to blue shift even more rapidly than the anisotropy. Namely, the power has to be greater than 1 in this case, so that the power is greater than 6. So you need a collapsing phase with an equation of state W much greater or greater than 1 at the very least. Now this is very interesting. If you consider just a component which has constant equation of state, of course the scale factor, the solution is this one, some power law. For W greater than 1, you can see the power is very small, because it's 1 over W. So you're led to a universe which actually is very slowly contracting as you make W larger and larger. And again, such a universe, even though you're collapsing, it's making the universe increasingly isotropic. And as a result, also makes all these other components completely irrelevant. It becomes a universe which, although it's collapsing, which you think is getting crazier and messier, in fact is getting smoother, emptier, and more symmetric.
Do you know that you've got the dot in there? There's no other terms one could dream up that go like, well, we're at the 7th or 8th. I mean, it looks like you've got a Taylor expansion.
Beautiful, yeah. So, in fact, these are the most common components. This one is exotic. So there's no typical component that goes from 1 over 8 to 7, for example. Isotropy is the one that has the largest power in usual forms of matter.
That's a complete list of everything
that you usually think about. Right, exactly. So this guy ends up being exotic.
This topic even in one, should this show up on in other expert physical contexts, neutron stars, so whenever you have very dense matter?
Ah, very nice. So this field could be very interesting. The conservative assumption, just like for inflation, is that this field is actually very massive. So by today's time, it has a huge mass, doesn't participate in processes. But it could be very interesting. Of course, locally, so this is for the homogeneous component, locally it could have very different properties. So certainly today, so to have such an equation of state, as we'll see, it actually corresponds to a scalar field that's rolling down a steep potential. That has other consequences. Whereas today, it should be standing still somewhere and probably have a large mass. Yeah,
somehow the dynamics of that scalar field isn't involved in the entropy itself.
No, purely homogeneous. I'll show you in a sec where it comes from. In fact, I just wanted to point out.
Tracking.
So in fact, these statements I just made, these heuristic Freeman statements, were shown through numerical relativity calculations by these guys. So you can show with a scalar field that indeed most of the universe becomes smooth as time goes on, even though it's collapsing. So before we get to the precise story of what the scalar field does, I just want to point out, this phase of slow contraction, in fact, was a central element of the Ekpyrotic model that I worked on back when I was a graduate student, and since then. In a nutshell, this model is based or inspired by concepts in string theory and M theory, where all the matter, all the standard model fields that we see are confined to a brane, separated by an extra dimension, and at the other end there could be some other fields out there. Gravity, the point is that gravity can propagate through the extra dimension, but the standard model fields cannot. Yeah. The idea was that these branes initially are empty, but are drawn together by a very weak force. They're drawn together to pick up kinetic energy, and eventually they collide. When they collide, the collision is generically inelastic, and as a result, some energy is deposited in the form of matter and radiation on the brane. And that, from the point of view of a brane observer, would correspond to the Big Bang, the creation of the matter and radiation. These branes then fly apart, and then you're led to usual standard FRW evolution. In fact, these collisions can happen over and over again. I just want to draw your attention to the fact that you see these branes start out flat and parallel, but as they come together, they develop ripples. So classically, if you start parallel, you stay parallel, but quantum mechanics tells you that things fluctuate. So in fact, you develop fluctuations, and as the branes fluctuate, this will cause the collision of the branes to occur at slightly different times, slightly different regions of the brane. That is eventually what corresponds to temperature and level.
When do they start parallel?
Very nice. So our original motivation is that branes that are flat and parallel corresponds to BPS solution. It corresponds to supersymmetric solution. So we wanted to say, maybe the initial state of the universe happens to be symmetric. In fact, when we looked at the problem more closely, you showed that in fact it's an attractor to be flat. Just by the same argument that it's a smoothing mechanism. So even if you had some ripples, just like inflation, a particular region of space will collapse more slowly if it happens to be on this solution.
So
and hence,
plays an important role in that?
well, good. So if you just say, I want to start flat and parallel, then you have to rely on supersymmetry, which is a very nice way to motivate the initial condition. But then you have an attractor, so you can say even if it has departures from it, it's an attractor mechanism. So we can give.
I'm a stupid particle theorist. I know nothing about these things, so.
No, great. That's great. Oh, sorry. You don't have another question?
No.
More later. Okay, good.
Yeah. Just more.
No, this is good. I'm happy to talk. That's why I'm here. So now, of course, we give this fancy story in terms of string theory, but there's a very basic mechanism that you can explain in terms of a 3+1 dimensional effective theory, so just ordinary scalar field in 3+1 dimensional space. Namely, if you have low enough energies that you don't resolve what's going on between the branes, you can describe this as an effective description of just a scalar field, which measures the distance between the branes. The required potential for the dynamics of what we are considering is some steep negative potential of this generic form. So as the branes are coming together, the scalar field is just rolling down this steep negative potential. This potential indeed corresponds to slow contraction. More generally, the equation, if you remember just the expression that we had for the equation of state, it's a trivial inequality. If the potential is negative, this equation of state is greater than 1. So any motion down a negative potential leads you to an equation of state greater than 1 and hence slow contraction by an earlier argument. This is pretty startling. I mean, this is startling. And the first time I encountered this, I was pretty startled because this is exactly the opposite of inflation. You couldn't have dreamt up something more opposite to inflation. In the sense that inflation requires positive potential that's flat to drive rapid expansion. This guy requires steep and negative potential to drive slow contraction.
What happens when the field gets large negative values of order of Planck fields?
So you never make it there. So you have to turn things around. You have to, you bottom it up just like inflation.
I see.
You don't want to stay in that phase for too long. Yeah. So in fact, one way we motivated this is you can have a minimum, potential rises back up, and that's how the story goes. Just like inflation, the process has to terminate eventually. So that was the story for the background. These are the only two possibilities that I'm aware of that make the universe smooth, homogeneous, isotropic, etc. What about inhomogeneities? So inhomogeneities are also very symmetric. They're the simplest you could have ever dreamed about. Their two-point function is nearly scale invariant. So if you parameterize a two-point function in the Fourier space in terms of the power spectrum that we measure is well fitted by a power law, k to the ns minus 1, and ns happens to be very close to 1. In other words, the power is scale invariant, strictly scale invariant in the sense that it's k to the 0, so a good approximation. And of course, ns is not exactly 1, which gives us a hint that in fact there was some dynamics going on in the Earth universe that produced these perturbations. The perturbations are also exquisitely Gaussian, and that's parameterized by a parameter FNL as the dimensional skewness of the temperature. And what FNL does, so this is just a schematic to show what turning on. This is a Gaussian realization of the microwave background, and as you crank up FNL, the map becomes manifestly increasingly non-Gaussian. There's definitely more extreme cold spots relative to extreme hot spots. The variance is the same, but you've introduced a large skewness, and by the conventions I've used, positive FNL corresponds to negative skewness for the temperature. Yes.
Sorry, I did the disclaimer already. But all this is happening on the face of the field is going towards the origin, right?
So far, this is modeled in this is observations, but okay.
No, but
yeah, these perturbations are created as the field is rolling. Yeah.
What happens when it starts going?
Very good. So this is maybe I come back to that later. Okay. So there's a long story to be told there.
Oh, and
but essentially, the physics is very simple. It's again extremely analogous to inflation. The perturbations you produce are stretched on scales much larger than the Hubble horizon at the time when this process is taking place. So you're on scales exponentially larger, just like inflation is. These models have a collapsing phase, and so you have to go through some kind of transition to an expanding phase. But the point is that because these perturbations have wavelength which is much larger than the causal scale, you are in some sense insensitive to the details of the bounce, in the same way that you're insensitive to reheating during inflation.
So somehow this effective field theory should never break down, in the sense that you don't have a singularity or anything like that.
Beautiful. Let's come back to that. Okay? We'll come back to that a little bit later on, and I'm happy to entertain this very nice discussion. Okay? But let's stick to observations for a minute. The constraints on this parameter FNL for the WMAP data are these ones. It's constrained to be less than 100 at the 2 sigma level, which is a remarkable level of Gaussianity. This parameter is thus defined corresponds to 0.1%. At 100, FNL of 100 corresponds to 0.1% deviation from Gaussianity. So it's pretty impressive that we're so close to a Gaussian spectrum. And of course, the final word, or let's say one of the most important words, will come from Planck. We'll get down to the FNL of 5. So this is very exciting time.
So what
Yes.
happens when FNL decreases becomes constant 0?
It corresponds to positive skewness. So it's the other way around. Right. So this is just a bound. Interestingly enough, this bound of course has been shrinking, but the central value, whatever that's worth, has stuck around 40. Whatever that means. There's no statistical significance to that statement, but it's temporal. So we'll see what happens with Planck. Okay, so now I want to discuss a little bit how inflation and other theories explain these properties of the perturbations. And most of you are familiar with these derivations of how perturbations are generated during inflation, but I want to provide what is somewhat perhaps a different point of view than maybe what you've seen before. Maybe you've seen this before. And I want to focus basically on the symmetries of the inflationary spacetime to explain the properties of these perturbations. So this is the Sitter space that we've seen earlier. It's an exponentially expanding metric. The Sitter space has a lot of symmetries. It's one of the maximally symmetric spaces in 3+1 dimensions. It has 10 symmetries. And these isometries of the Sitter space, if you wait at late times, mainly when we compute correlation functions at the end of the day, at late times, these isometries, they actually act as conformal transformations on the plane. So this is well known, for example, to string theorists who looked up the Sitter CFD or think about the Sitter CFD correspondence. There's this map between the isometries of the Sitter space and conformal transformations at late times. So what are the conformal transformations? They of course correspond to translations and rotations in the plane. There's also dilatation. And there are 3 conformal transformations which are the special conformal transformations. So of course dilatation, we know what they do. They just expand. Special conformal transformations are less intuitive, but roughly speaking, they correspond to doing an inversion, bringing points to infinity close to the origin and vice versa, followed by a translation, followed by another inversion. That's as much intuition as I can give. I don't have more. So there are these 10 symmetries, and these 10 symmetries form, their commutation relations form the SO41 algebra, which is the same, of course, as properties of the Sitter space. So that's the statement of the symmetries of inflation. Now, of course, we were interested in computing correlation functions of various fields at late times in inflation. So at late times, indeed, we should have that our correlation functions should be invariant under these conformal symmetries. So purely based on symmetries, we can guess the form of correlators. So if you have any spectator field in inflation, so some field in the game which doesn't participate in the background dynamics, so that's important because inflation, the inflaton itself will be an important exception to that statement. So any other field, for example, any other spectator scalar field, will acquire a two-point function which is determined by conformal invariance. It's just a function of the distance to a particular power, which is the conformal weight. That conformal weight is given by the ratio of the mass to the Hubble parameter during inflation. So in particular, without solving anything, you know that any field whose mass is much less than Hubble during inflation will acquire a nearly scale invariant spectrum, which becomes independent of scale. This includes in particular gravitational waves. These are massive degrees of freedom. And that's the point that was stressed in particular. So I should say these arguments, by the way, go back a long time to a paper from 1997 by Antoniadis and collaborators. More recently, Maldacena did a lot of nice work to compute the three-point function of gravitational waves, and he used precisely these arguments. Indeed, the three-point function is also fixed by the symmetry. So the three-point function of conformal field theory in 3 dimensions looks like this. It's some particular combination of the distances between the 3 points involved. And there's only one free parameter, which is the overall normalization of that three-point function. So it's greatly constrained, is the point. Okay, so this was all true, again, for spectator fields. If you have other fields during inflation that are somehow participating in generating the observed density perturbations. I want to move on to the work that we've been doing, which is what happens to the perturbations of the inflaton itself, this exceptionary guy. In particular, we're interested in single field model, where there's basically one agent, one scalar field, which is both driving the background and generating the perturbations. Now, already intuitively, first of all, we've said already we don't want the Sitter space to last forever. It has to terminate. Hence, this phi is a clock to tell us when inflation is going to end. Moreover, precisely because we're talking about fluctuations of this field, clearly the fluctuations are sensitive to the fact that you're not exactly in the Sitter space, but that inflation must end. So the perturbations of the inflaton are clearly sensitive to the fact that there is not exactly Sitter space. So one way to think about it is that the conformal symmetries that we were talking about, the conformal symmetries on the plane, are in fact spontaneously broken by the inflaton. So in fact, the correlation functions of the inflaton will be precisely directly sensitive to the symmetry breaking, as we'll see in a second. So the take-home message, what we want to say, is that the SO41 symmetries of the Sitter space, these conformal symmetries, they get spontaneously broken down to rotations, spatial rotations and spatial translations. That's how you should think about single field inflation. Now I want to say how to see this explicitly, especially for cosmologists, how you see this explicitly, that this is the symmetry breaking pattern that's taking place. So the nicest gauge probably to describe perturbations during inflation is co-moving gauge. This is a gauge, a choice of time slices, for which the scalar field, the inflaton, is unperturbed. So you're precisely choosing surfaces, so your surfaces of constant time are precisely surfaces of constant phi. I should say these are all scalar perturbations. I'm not worried about tensors for now. You choose constant phi surfaces, constant density surfaces as your surface of constant time, and you can use residual gauge freedom to set the spatial metric on each of these slices to be conformally flat. So namely, it's just some function of time at x proportional to the Euclidean metric, delta ij. That's known as the comoving gauge, and the corresponding zeta here captures all the perturbation, and it's called the curvature perturbation. Curvature perturbation because it's perturbation precisely in the curvature of these slices. That zeta at the linear level was introduced by these guys, Bartenstein, Harman, Turner, and I wanted to tip my hat to Dick because in fact he was the first to consider these nonlinear form, this exponential of zeta, in the paper with Sal. Now, in this gauge, actually, the symmetries I just discussed are manifest. Suppose you do a conformal transformation on the plane, so purely spatial transformation, which maps delta ij to delta ij times some function of x. Because it's a purely spatial transformation, clearly it doesn't change the fact that the surfaces remain surfaces of constant phi. It doesn't mix what time is. But it does change the form of the spatial metric in this particular way. On the other hand, this still maintains the form to be conformally flat. You just shift zeta. So it's clear that just by shifting zeta, redefining zeta, you can absorb such a transformation, such a conformal factor. That's the symmetry. So to be explicit, the dilatation symmetry and the special conformal transformations are understood as transformations on zeta in this particular way. And in the particle physics language, we would say that these symmetries are non-linearly realized because the transformation of the field is not proportional to the field itself, but it's shifting by a constant. At least that's field independent. So the symmetry is definitely spontaneously broken, but it's there. Now, here's the puzzle, because cosmologists, your immediate worry are twofold. First worry is, hold on a second. I'm taught that co-moving gauge completely fixes the gauge. So what am I talking about when I say that I can perform a transformation which shifts the form of the metric? Now, carefully, of course, when you say completely fixes the gauge, if you look carefully, you have in the back of your mind gauge transformations that fall off suitably at infinity. That fall off. Of course, conformal transformations are an obvious loophole because conformal transformations, of course, dilatation acts all the way to infinity. And special conformal transformations maps infinity to the origin, etc. So, in fact, this is a loophole to the usual assumption that the gauge transformation falls to infinity. Similarly, you're also taught that zeta is a gauge invariant variable. You can define a zeta, which is gauge invariant. So what am I talking about when I say that zeta shifts? So again, that's one of those things that gets you puzzled for a couple of days, but then you realize that in fact these gauge invariant variables, they're again defined so that they're gauge invariant again for gauge transformations that fall off at infinity. So again, that's the loophole of the argument. So this is completely consistent with what we usually think about. Now, forget about these arguments. You can just say, this is my proposed symmetry. Here's the action for zeta. It's been computed by Maldacena in particular, this cubic action. This is the quadratic action. It's a mess. But you can go ahead and you can check that if you perform these transformations on zeta, it's a symmetry of the action. So you can stop arguing with yourself. Unambiguously, it's an invariance. So again, now it's clear that in fact the Goldstone boson for the symmetry breaking is zeta. It's a natural definition. Zeta is the dilaton for these broken conformal transformations. So it's the dilaton for the symmetry breaking pattern. Note in particular, in fact, that if you're familiar with Goldstone's theorem, you find that here we have 10 original symmetries. They get broken down to 6, 3 rotations, 3 translations. Yet I'm claiming there's only one Goldstone. So it seems to break the usual counting with Goldstone boson. So that's well known. The usual counting works for internal symmetries. When you have space-time symmetries, the counting doesn't work. There are degeneracies. So here you can have a single field which accounts for 4 Roman symmetries. That's completely consistent. That's your dilaton. So what? What's the point of the symmetry insight? Well, of course, we're claiming there are 4 broken symmetries. But these symmetries, they may be broken, but correlation functions will know about them. Correlation functions will know about them in the form of Ward identities. So Ward identities for broken symmetries, they take the form of an n-point correlation function being related to an n-1 point correlation function. If the symmetry is not broken, what you would have is just a statement about the n-point function itself. When it's broken, it's a statement between relating n-point to n-1 point function. And that's the structure, of course, of the soft pion theorems of the strong interaction, where you add a soft pion to a process, relating the correlation function or the amplitude with the soft pion and without the soft pion. So there should be such relations in cosmology. Can you think of one? So there's one relation that is eerily reminiscent of this, and that's the consistency relation. So Maldacena, in his famous paper on non-Gaussianities, found the following result. He found that if you compute the 3-point function for zeta in momentum space, for simplicity, for 3 momenta k1, k2, k3, and you consider the limit where one of the k's goes to 0. So observationally, naively, what that corresponds to is you take 3 points in real space, and you take 2 of them to be close together and the other one far apart. That momentum space corresponds to taking one of the case to 0. And he found that in that particular limit, up to an irrelevant momentum conserving delta function, the 3-point function degenerates to something universal. Namely, it's just the spectral tilt of the spectrum, and S minus 1, which is of course few%, we know that, times the product of the power spectra of the long wavelength guy, the short wavelength guy. So it's precisely of the form 3-point function gets related to 2-point function. This theorem, first of all, the ringing bell for me was the fact that it's precisely a limit where k goes to 0. So it is reminiscent of soft, we call it soft CITA theorem. You're taking one of the z's to be very soft. It's a very powerful theorem. It holds for all single field inflationary models. I can't stress that enough. All single field models. Any field, any single, not even single field, single degree of freedom model has to obey this identity. So in particular, flip it around, if we were to measure a 3-point function which is significant, far larger than this few% level, in this particular limit, we would immediately rule out all single field inflationary models. All of them. It's an extremely powerful theorem. In reality, it's been proved either by brute force argument, where you actually take the action, you compute it, the way Maldacena did. You can also give background wave argument, which I'm happy to go into, some causality argument for why 2-point in the presence of a long mode should behave in this particular way. You should obey this identity. But to me, it's clear that this identity is so fundamental, so powerful, that we have to find out exactly where it comes from. So we have a hint, we're in progress, figuring out where it comes from. So I should have said this work is done with postdoc at Penn, in particular, and Khoury at Columbia. So we think that this consistency relation is precisely an example of the Ward identities that I schematically showed earlier. We think it's the Ward identity related to broken dilatation. So schematically, the Ward identity that we're looking at takes the following form. It's a correlation function between the conserved charge Q, the conserved charge of the dilatation, and 2 zetas. And the Ward identity relates this 3-point function to the derivative with respect to the log of the distance of the 2-point function. That, in momentum space, corresponds precisely to taking bringing down an ns-1 factor. It's just a derivative with respect to scale of the power spectrum. Now, of course, the meat of the problem, which has kept us sweating for the last 6 months, is how to turn a statement that involves Q, which involves the canonical momentum to zeta, into some statement, and you have to take the imaginary part, turning this into a statement about the 3-point function of zeta. That is highly non-trivial. At 95% confidence level, I can tell you I think it works, but it's still keeping us up at night. Okay? But such a statement we think is possible. That in the end, it's just in disguise some Ward identity in this way. And it's not surprising you have to work hard, because these formal statements, to get some useful information observationally, you have to work hard to put them into some form like this. Why should you care? Why should we bother about this? Because Ward identities are very powerful. They're non-perturbative statements. They're just statements about symmetries. So this would give consistency relation a firm footing, in my opinion. Moreover, there will be more consistency relations. These are just for dilatation, but you also have special conformal transformations, 3 of them that you've broken. These will lead to their own consistency statements, with which you can use to completely rule out inflation in principle. So there's a whole network of consistency relations. This one was easy to compute, well, not easy, but you had the cubic action, you could compute it, you could find this statement. But at higher point level, it becomes very messy. So these kinds of symmetry arguments are very powerful. And I'm happy to take questions on tensor modes. That's something we've also been thinking about. This is all scalar sector, but there's also symmetries associated with gravitational waves. What about non-inflationary models? Okay, this was all inflation. So I want to first tell you a theorem if we're going to move away from inflation. So let's start with a theorem that, so this is a theorem that I proved with my students, Godfrey Miller and Austin Joyce, and the results independently were found by Daniel Baumann, Leonardo Senatori, and Matsuo Salvariac. Here's a statement. Here's a theorem. The theorem is very simple. The theorem says that inflation is a unique mechanism with the critical assumptions you have 1 degree of freedom, so 1 scalar field of any 1 single degree of freedom, on a background that's a dynamical attractor. That's another important feature. So single field, attractive background. Inflation is a unique mechanism that's capable of generating scale invariant and Gaussian perturbations over a broad range of states. That's the statement. Okay? Broad, I mean more than 10 to the 4, 10 to the 5 in K space. Let me just sketch, I won't sketch the proof because it's a little boring, but I can tell you the key steps. If you assume the extra assumption that the sound speed is unity, so your whatever perturbations you have for this degree of freedom have unit sound speed, then the combined assumptions of scale invariance and attractor gives you only two possibilities. One is inflation, of course, where the scale factor expands exponentially and you have a constant equation of state. The other possibility is something that I derived with Paul Steinhardt. We call it the Ekpyrotic scenario. The scale factor stays nearly constant, but the equation of state is dramatically changing. It's the exact opposite. You see, in one case, the scale factor is changing dramatically, the equation of state is constant, the other way around here. These two phases have identical two-point functions, indistinguishable two-point functions. But when you look at the three-point function, because this scenario relies on a rapidly changing equation of state, it corresponds to a rapidly scale-dependent or strongly scale-dependent FNL. So as you go to small scales, basically your FNL grows very large. Eventually, you have highly non-Gaussian perturbations. So that's the loophole. So only inflation, if you want, is possible with CS equals 1. And in fact, we've generalized, with my student Austin, we've generalized this to an arbitrary sound speed, arbitrary time-dependent sound speed. So, what's the upshot? The upshot is the following. If you want to produce nearly scale invariant and Gaussian perturbations over a very broad range of modes, you have three options at your disposal. Either it's inflation, or you give up on this assumption of dynamical attractor, you consider unstable solutions, or you have to consider multi-fields, theories whose perturbations are generated by some other field in the story. So of course, we want to keep the stability, and we're going to consider multi-field mechanisms. Now your reaction might be, oh, you're giving up on economy, right? You're going to start throwing in more field in the story. The claim that I'm going to show is as long as things are governed by symmetries, then it's okay to consider more multi-fields. As long as you're not tuning things to make scale invariance and Gaussian. So I want to discuss with you an alternative to inflation that we've been working on for the past year, which is called the Pseudo-Conformal universe, which I find quite promising. So this is work done with my postdoc Kurt Riegler and also my student Austin Joyce.
But just to
Yes,
backtrack a bit, does this mean that there is some basic instances between the Ekpyrotic scenario and
Very nice question.
the Gaussian?
Very nice. So the Ekpyrotic scenario with a single scalar field that I showed you earlier does not give a scale invariant spectrum under usual assumptions. Okay, under the usual assumptions, the curvature perturbation is not scale invariant. There are, so later versions of the Ekpyrotic scenario that I worked on with Bert Overt has two scalar fields, and then it's fine. Yeah, thank you for that question. Right. Pseudo-Conformal Cosmology will have a lot in common with Ekpyrotic Cosmology, it turns out. So here are the basic ideas. First of all, of course, it's a non-inflationary scenario. The dynamics takes place before the Big Bang. In fact, for all intents and purposes, the space-time is static. So you can think of this as happening in Minkowski space, flat Minkowski space. Now Minkowski space is familiar to all of us. It's the arena of special relativity. It has as many symmetries as de Sitter space. It has 4 space-time translations, 6 Lorentz transformations. But we need more symmetries to make the scenario work. We're going to assume that in fact the theory is conformal, or nearly conformal in space-time, meaning there's also one dilatation, space-time dilatation symmetry, and 4 special conformal transformations. These are 15 symmetries. It's the most symmetric scenario we've seen since Protocol. Okay? That's the scenario we're considering. 15 symmetries, and these form, of course, the algebra of SO4. So just to make it concrete, here's the simplest version of the scenario. Consider a scalar field, phi, which is rolling down a negative quartic potential. This is a solution that was studied by these guys in some other contexts, and in particular by Rubikov in this context. This is in Minkowski space, okay? So first of all, a phi to the 4th theory is classically conformally invariant. Moreover, a negative phi to the 4th is actually asymptotically free. So this is the theory we're going to start discussing. Everything is happening on flat space, so there's no gravity. Energy is conserved. So if you take the solution which is homogeneous, then you have a conservation line. Of course, the conservation of the energy of the particle rolling down. is constant. And here's the difference between kinetic and potential, or potential and negative. So here it is. The solution which has zero energy is this one, where time goes from minus infinity to 0. So it corresponds to a solution which asymptotically in the past had the field starting at the top of the hill and rolling down subsequently. That solution is actually an attractor. Looks fine-tuned to begin with, but it's an attractor and it's easy to understand because think about it. You take a scalar field with the particle, let's say, you make it roll down. Suppose E is non-zero to begin with through some other solution. As the field rolls down, its kinetic energy grows in magnitude, so does the potential grows in magnitude, such that this tiny energy to begin with was completely irrelevant. So it's a dynamical attractor. Another way to say this is a perturbation with some finite energy at late times gets reabsorbed into a shift of time of this solution. That's what comes out. The growing mode is just a constant time shift of the background. So it's a dynamical attractor. In particular, because the potential is negative, this precisely falls into the class of potential that we discussed earlier. The equation of state is larger than 1. We'll show that explicitly later. But it means immediately that we know it corresponds to a, although there was no gravity in this story, but if you turn on gravity, you will end up with a universe that's very slowly contracting. So it's consistent to take it to be flat to begin with, and as a result, it makes the universe increasingly smooth. That solution, the 1/T solution, actually breaks 5 symmetries. It clearly breaks time translation symmetry. It breaks all the boosts. And it also breaks the one special conformal transformation along time. So there are 5 broken symmetries. You can convince yourself that's the case. So the symmetry breaking pattern in this theory is that the 15 symmetries of the conformal group, the conformal algebra, get broken down to 10 symmetries. And those symmetries, remarkably, form SO41. So the unbroken symmetries are SO41. These symmetries, these unbroken symmetries, are precisely those of the de Sitter space. They're the same as the de Sitter symmetry. So not surprisingly, you're going to have certain fields in the ballgame will acquire scaling variant perturbations. But keep in mind, there's no de Sitter expansion. These SO4 symmetries have nothing to do with gravity. They're purely space-time symmetries on flat space. Okay? So that's the argument. Now, we can make the scenario more general. I'm just going to skip over that. Pardon? Okay, good. So now let's go back. Yeah, so I should talk about the end before I get to the end. So eventually, same story. You have to turn this around because you never want these spaces to last forever. Yeah. We're never going to be here. So you have to assume there's some turnaround in this potential, and that's natural, as I'll show in a second, because this assumption, in any case, that things are, these solutions are as if there's no gravity, that precisely breaks down when the field reaches values of order Planck scale. So that's precisely we expect higher dimensional operators, Planck suppressed higher dimensional operators to change the potential in any case. So now you have to be optimistic that these guys make the potential turnaround. But that's the point. The point is, on the other hand, nothing about the perturbations you generate over here, which is what you observe, is sensitive to what you do over here. So that's exactly like inflation. I mean, you could say in inflation, why in the world does the thing have a minimum? It better have a minimum, otherwise you wouldn't be here. That's the answer. But the point is that your existence doesn't care about the details of how this minimum looks like. Similarly, so that's the usual story. All right, I'm going to skip over that. You can make the scenario more general. Yes.
You can make a turnaround.
Well, the potential is negative throughout. So.
It's a constant.
Oh, but it makes a huge difference for the cosmology. So in this case, you'll see. So the only thing that cares about the constant is gravity. In this case, the universe is slowly contracting.
Okay, so just whether.
Yeah, of course, yeah, good point. So in this case, you're not going to stay stuck. You're going to exactly. So you have to roll off and end up somewhere else in the potential. Right. The key point is you don't want to end up all the way down. Yeah. Thank you. That's important. Okay, I'm going to skip that. You can make the scenario more general by having many fields. The main thing I want to emphasize is that although I gave you a specific scenario, the scenario is very general in the sense that, as usual, much of the physics is captured just by the symmetries that are involved, just by the symmetry breaking pattern of SO42 going to SO41, without having to do any statement about the detailed macrophysics, whether it's this potential, that potential, as long as you have fields in the theory that acquire profiles of this type, 1/T to their conformal weight, you will achieve this symmetry breaking pattern. So in particular, you can borrow the technology in particle physics to write down the most general effective theory for the perturbations of this theory. So That's what we did. You can write down, there also in here, there's only one goldstone boson. Again, even though we're breaking by symmetries, there's one dilaton if you wish. And the action for the goldstone boson, we can write it down, through arbitrary order. This is it. And in fact, so this theory linearly realizes, if you want, these de Sitter symmetries, SO41, and the goldstone non-linearly realizes these SO42 symmetries. So that's the theory for the goldstone. And then you can discuss other fields that you can throw in, such as some other field chi, some weights.
So what if there is some small explicit break right in the parallel direction, since you mentioned that so much? What does it affect this field?
That's right. So now you're going to have, so now you're going to have some breaking of these. So these coefficients, of course, are related to each other to make, to ensure SO42. So now you're going to have some leading corrections. They can be Planck suppressed, for example.
What about the mass terms?
You can have a small mass term. In fact, it has a small mass. Tachyonic mass. So you have correction to the tachyonic mass. Interestingly enough, by the way, this guy has a mass. Again, because it's not a goldstone for internal symmetry, it doesn't have to be massless. So be it. So under a very general assumption, if chi has small mass, it will acquire scale invariant perturbations. You can show that. So that's again generic conclusion from effective theory. Is it distinguishable from inflation? That's the key question. So now, it has the same SO41 symmetries as spectator fields in inflation. So in particular, 2-point function and all the higher point functions have the same structure that we saw earlier for spectator fields in inflation. So at that level, we say it's indistinguishable. But of course, it has more symmetries than inflation. It has these SO42 symmetries that have been broken. There are 5 symmetries. So correspondingly, there should be some Ward identities, again, for these 5 broken symmetries, relating endpoint functions of these spectator fields with n-1 point functions. I don't know what these are. I can't even fathom what SO42 puts as a constraint on cosmological perturbation. But it will be very interesting to see. Maybe they're ill-defined, I don't know, but it's very exciting. There will be some additional constraints. For example, actually we found one already. If you take 3-point function, here I'll just write it down. If you take 3-point function of goldstone with 2 of these spectator fields, that we showed was linked, right? There's a normalization constant and some powers of the distance between the points. It's completely fixed in terms of one, call it C1, one normalization constant. 2-point function of chi gives you another normalization constant, and 2-point times some scaling factors that are obvious. And there's another normalization constant for 2-point function of pi. In a purely SO41 theory, these 3 parameters are independent, but SO42 gives you a link between these 3 guys. So there's going to be some constraint more generally between 3 points and 2 points. This one may not be useful, but in any case, it's a hint that there's more structure, more constraints. Inflation, of course, has a smaller symmetry group, so these relations are not necessary. They would be accidental. Let me just briefly address the story about turning on gravity. So here's what happens. So the simplest thing we do is we take the conformal field theory we described and couple it to Einstein-Hilbert gravity, breaking conformal invariance by the 1/n Planck level. We break it mildly. Again, you can make arguments completely just based on symmetries. At early times, as we'll show consistently, gravity is negligible. So you can immediately infer what the energy density and the pressure of your CFP should look like just based on the symmetries that are at play. The symmetries are dilatation invariants. So immediately you know, and everything's time dependent. So you know that both the energy density and the pressure will go as 1/t⁴, based on dilatation invariance. And energy is nearly conserved, so the energy density actually has 0 coefficient. So energy density is 0, pressure goes 1/t⁴. For the potential, product potential, is exactly what you get, particular coefficient. If you plug that into your cosmological equation, you find precisely Hubble parameter going as 1/t. T is very negative and large, so Hubble is very small, corresponding to your universe is nearly static. That's just to say that all these stories we were discussing earlier are consistent. The universe has an equation of state much larger than one corresponding to a nearly static evolution. Gravitational waves are another probe of the story. So this is a very generic argument. Inflation, of course, because of its rapid expansion, excites all light fields, including gravity waves. And there are I can make some argument if you want about why I expect gravity waves to be observable at the level of R.2. So you should expect scale invariant primordial gravitational waves in inflation. Because inflation is very democratic, is the point. Whereas the pseudo-conformal Ekpyrotic model, they all correspond to very slow contraction, and correspondingly, you don't appreciably excite gravitational waves. you find a very blue spectrum of gravitational waves that are completely unobservable. So directly, if you were to detect primordial gravitational waves, say with SPIDER, this would immediately rule out all these pre-Big Bang ideas right off the bat. Here are my conclusions. So well, the take-home message is that, first of all, the large-scale symmetries of our universe, homogeneity, isotropy, and flatness, can be reproduced by only two phases, to my knowledge. One is the rapid expansion shortly after the Big Bang that inflation produces, or a phase of slow contraction long before the Big Bang. Again, the underlying words are exact mirror images of each other, right? That breaks down when you talk about gravity waves. One guy produces significant gravity waves, the other does not. And at the level of density perturbations, we've classified these different ideas in terms of their symmetry breaking patterns. So multi-field inflation, where you have scalar fields that are spectator fields, have unbroken SO41 symmetries. If you're talking about the inflaton, you have a symmetry breaking pattern where SO41 goes to spatial rotations and spatial translations. And then this alternative that we discussed, the pseudo-conformal universe, invokes more symmetries. It relies on SO42 getting breaking down to SO41. And these symmetries, as we've argued, will get reflected in the correlation functions. Thank you very much.
Then back to theory that you wrote, I'm sorry. We're back into the prior field. What was the mass scale? You didn't have any mass scale on the way down. And then you said there was a mass.
It's 1 over t squared. 1 over t.
I see.
So intuitively, very naively, of course, the negative coordinate provides you the thing to keep in the back of your head.
Yeah.
The mass grows as you go down the potential. It goes as 1 over t.
Does this cracked universe scenario have anything to say about why there are big macroscopic spatial dimensions? I mean, when you generalize this Taylor expansion to 4, 5, 6, does anything?
Oh, that's a nice question. Right, that's a nice question. Yeah, so that's a very nice question. So in fact, I wasn't involved in that work, but there was some work done by students of Paul Steinhardt and Paul Steinhardt. What they were looking at are precisely this issue of chaos, DKL chaos, as you approach a crunch. And whether you generate chaos or not has to do with the field content, in particular how many dimensions there are, what kind of form field there will be from string theory. So they looked precisely. They did some studies, but the intuition behind their work was indeed something similar to what you're saying. Namely, there will be some particular cases where you can avoid chaos, other cases where you can't. Maybe that's a selection mechanism, pick 3 large dimensions at the end of the day. That was their motivation.
So in the standard inflation picture, there's still really an explanation.
For the 3 large extra dimensions, there's some ideas, right, but not the nothing strict in balance. No,
that's goes well beyond it.
And in string theory, you have to assume these extra dimensions are compacted by why they started out compacted by. I mean, there's some ideas, but not completely robust. Yeah. That's a big puzzle.
First question. You mentioned that with respect to this field in the closet consider, you've got a predation just from the component field that it will run the 3-point function should be.
Yes.
But that's just the 3-point function for actually the 3-point function in the field itself, not the 3-point function.
Good.
Curvature perturbation.
Yes, right.
That
We
can
observe.
Right. For example, like the Curvaton scenario, there's negligible
Right.
sigma, but
Right.
you get large
Very nice,
point.
very nice, very nice. So,
Is there any way to see that connection from the symmetries, or does that have to be put in later as a post-processing after horizon crossing source of non-Gaussianity and multiple?
good. So it's an additional contribution. Now, that 3-point function I showed you, the story is pretty subtle, but it actually contains a local part into it. So now when you do the conversion, the nice thing about the conversion is it's a local process in all cases. So you generate the local shape additional to this. That, in particular, is particularly worrisome, for example, in this case, with these other relations that one can derive. There will be likely some contamination. But you know what it is, it's local. So best case scenario is that you can actually disentangle the local piece from this piece.
So there will be a non-local piece that obeys the scalar relations.
Exactly,
that
and
are-
the local piece that
and a
will-
local piece that's
will-
separate.
That
and
is
you
separate.
put-
That's
you put
right.
separate
That's
out.
right. But you know, the only mechanisms that people usually consider, they're all causal. They're all local. You know what what the contamination is. Yeah, that's important.
So in this minus lambda part report, the one that you considered, you said that you're going to handle inflation on this process by suppressed operators. It looks to me that the effective field theory will break down vis-a-vis suppressed operators.
Absolutely. But I don't know, but you're not reaching.
You said nothing dependent on that, so it's hard to reconcile those two statements.
No, okay, very nice, very nice, very nice. So there are two scales at play in your, so there are two scales at play. So one is to do with one has to do with when the field theory, when the effective theory breaks down, okay, which indeed when the field reaches values of order n.
Yes, correct.
But the other parameter in town is the wavelength of your mode relative to the Hubble scale.
Okay.
So as long as, and this is a standard argument, so why, for example, in inflation you never care about what's happening to reheating, for example. It's very important because you want to connect to what you measure later on. And the point is that any evolution to your long scale perturbations are precisely suppressed by this ratio of k over the Hubble. So k wave number is tremendously small, exponentially small. And this is tied to the attractive property you can show rigorously. So as long as you say this unknown physics, whatever it is, all observers will follow the same history. That's precisely the same statement as saying that you're going to be insensitive to the details. So at the small scales, of course, you're right. It's going to be a mess. You never observe those modes.
I must say that from a particle thesis point of view, this minus lambda bracket report looked very strange. But
Really?
maybe it's okay.
Why is it strange?
Well,
First of all, it's the simplest theory you can ever dream about. More importantly,
it
this
doesn't have a ground state for one thing.
Ah, very nice. But cosmology doesn't care about ground states. We're always evolving, is the point. You guys do scattering experiments in cosmos space, but our universe is always time evolving. We don't care about ground states. That's the truth. You have to live with time-dependent backgrounds. No, but more seriously, just make a point about this. I'm happy with the fact that you're unhappy about phi to the fourth. The honest statement, just like inflation, all I've said in this talk, in terms of the perturbations, we're insensitive to what the precise model does to symmetry breaking. That's the take-home message. Whatever, and I wrote it for here, whenever you have a conformal field theory, such that certain scalar operators pick up precisely this time-dependent expectation values, you will get this prediction. So then it's a statement whether you like these symmetries. Yeah. So it's like saying, yeah. It's like saying, I don't like UCD, but I like the pi over run. Okay. Thank you very much.